Toward a New Electromagnetics. Part 3, Clarifying the Vector Concept. 1983 TE. Bearden. Implications. Some of the fundamental concepts of the new Tesla electromagnetics are presented. The new concepts have startling implications. 1. No force or force field exists as such in vacuum. 2. Hertzian, transverse, electromagnetic waves do not travel through the vacuum, just as Tesla stated. 3. Forceless, massless Tesla, scalar, longitudinal waves actually transit the vacuum. Tesla called them electrical sound waves. 4. At present there are actually 4 different fundamental types of vectorial entities in physics, erroneously confused as one and the same. 5. Tesla longitudinal scalar waves are also time waves and can affect anything and everything that exists in time. 6. The fundamental constants of nature, which exist in time, can be altered by Tesla scalar waves, which oscillate the values of the constants. 7. Every vector and scalar has an internal substructure, which can be independently affected and changed. This allows the direct engineering of the virtual state and the vacuum itself. 8. All observable forces, electrical, mechanical, gravitational, etc., arise in, on, and of the actual substructure of the accelerating mass particle itself, not as an external massless force or force field applied to a mass. 9. Physical reality itself, and the physical laws of nature can be deliberately changed and engineered. 10. All physical reality is totally internal to the physical changes of the mass particles of the detector system of the observer. 11. Relativity's speed of light limitation applies only to the changes of the basic mass particles of the detecting instrument. 12. Detection of superluminal effects cannot be accomplished by a single stage or single shift, single interaction, detector. 13. Detection of superluminal effects is permitted by multiple stage or multiple shift interactions where the last interaction is a conventional interaction of photon versus detector particle. The two-slit apparatus for detection of electron diffraction is an example. First, the superluminal de Broglie waves interact with the slits, which are tuned toward the electron's de Broglie wavelength. The interaction with two slits produces subliminal interference effects, which then interact back upon the physical electron. The apparatus is thus an electron interferometer capable of detecting superluminal waves by a two-stage interaction. 14. Interference is the most common first-stage superluminal interaction to accomplish downshifting superluminal entities to luminal or subliminal velocities. Superposition of superluminal phase waves, such as de Broglie waves, which individually always move faster than the speed of light, interferes the waves to create a subliminal group velocity, which may then interact with an ordinary mass particle in the detection system. 15. Any otherwise physical vector must exist as an unzipped, segmented, or shadow vector in vacuum. Radiation of a vector M wave from the electron gas in an antenna into vacuum results in the choking off of the mass of the transversely oscillating electrons in the antenna. Since the spinning electron mass is the zipper that makes or comprises the physical vector in the first place, this throttling of the mass flow unzips the E and B vectors, leaving whirling, massless magnetic scalar potential, segments of massless charge flux, massless electrostatic scalar potential. This unzipped whirling pattern of charge flux, scalar massless A/, is what radiates into vacuum and propagates through it. This is a special kind of scalar wave pattern, not a physical or vector wave. 16. The spin of a charged particle is the mechanism for integrating or zipping together the individual virtual fragments of a shadow vector into a real, observable, vector. For uncharged particles such as neutrons, it is the spins of its virtual charged components that accomplish the integration or zipping. 17. All fundamental charged particles are constantly accelerated. There is no such thing as an unaccelerated particle, except as a gross average over time or length. Further, all of them are spinning. 18. All changes to and from a physical vector or scalar system must arise in and come from its own internal substructure, which is zipped to its spinning particle of mass. 19. All fundamental particles are charged internally. That is, they are dynamic assemblages of smaller charged particles. If the average sum of the total internal charge is essentially zero over some finite, small increment of time, the particle is externally uncharged. If the sum is not essentially zero, the particle is also externally charged. 20. There are no static physical things in existence. In physical reality, something appears static only at a particular level. Upon sufficiently fine examination, it is composed of accelerating parts, and thus comprised of fluctuations. 21. Since, a, the basic physical, mass, vector consists of a smeared particle, where particle and smear are inseparable, b, the conceptual particle also is accelerated, and, c, the smearing is for a small increment of time and a small increment of length, then the basic constituency of physical reality is inseparable force x time x length, or action. The basic quantum of physical change is thus comprised of action. 22. Since to detect we must stop the action, separate or split the quantum into two pieces, canonical pieces, and compare, measure, one piece by throwing away the other, then each physical observable must have a differential operator, the separating agent, corresponding to it. This accounts for the fundamental postulate of quantum mechanics whereby every observable has a corresponding operator. Further, since what remains is totally relative to what was split out and thrown away, physical change is totally relative. This accounts for the fact that observed reality is relative, each part to each other. 23. As a special case, we may assume that we can evaluate a physical change at a point, without length. If so, when we discard length, the remaining basic vector is momentum. This approximation holds only so long as the system to which it is applied essentially does not change over the quantal fragment of length discarded, i.e., it holds for the linear case. Conservation of momentum, then, is violated when sufficient nonlinearity in length is present. 24. As a second special case, we may assume that we can evaluate a physical change in a spatial manner, without time. If so, when we discard time, the remaining basic vector is energy, has the units of energy or work. This approximation holds only so long as the system to which it is applied essentially does not change over the quantal fragment of time discarded, i.e., it holds for the linear case. Conservation of energy, then, is violated when sufficient nonlinearity in time is present. Since a virtual change a priori is defined as a total nonlinearity in the observer's quantal time increment but not outside it, then virtual interactions can and do violate conservation of energy within that time increment, but not out of it, so long as the time interval itself is considered linear. If the time interval is sufficiently nonlinear, then the virtual change may result in violation of the conservation of energy externally to the time increment. In that case, an observable change results. 25. As a third special case, we may assume that we can evaluate the instantaneous value of a physical change at a static point in space. To do so, we must discard both time, to be instantaneous, and length, to be at a spatial point, and the remaining basic vector is force. This approximation holds only so long as the system to which it is applied essentially does not change over the quantal fragment of time or the quantal fragment of length discarded. Conservation of force, then, is violated when sufficient nonlinearity in time or length is present. 26. A new conservation of energy law is required, one which unites the present conservation of energy law with an altered form of the conservation of charge law. Briefly, the total equivalent of mass, observable energy, and massless charge, an energy, is conserved. 27. All L and at fragments are produced and destroyed one at a time, in the action fissioning of a single quantum of action, detection process. Each L and T is discretized but not quantized. Since quanta do not superpose, the external universe is continually created and destroyed in the detector's mass system, one quantum at a time, at a very high rate. This interpretation gives physical meaning to the creation and annihilation operators of quantum mechanics. 28. Since the detecting mass system is itself continually created and destroyed one quantum at a time, ultimately all is mind changes, and only mind changes. The observer's life, mind, and being transcend all materialistic interpretations of reality, as indeed does the very fact of the existence of a perceived external universe. Electrical physics presently has a mindset. In examining the foundations of geometry, mechanics, and electromagnetics, it becomes strikingly clear that substantial, even grave theoretical errors were made early on and perpetuated into the existing theory. These errors are now so firmly entrenched that they form a part of the mindset of almost all physicists, engineers, and scientists. So ingrained are these errors and inconsistencies that the orthodox scientist/theoretician finds it almost impossible to break out of them. The present mindset is analogous to the Newtonian mindset which so fiercely resisted the new ideas of relativity, shortly after the turn of the century. However, after a few scientists formulated the rules and theory of the relativity mathematics game, a new generation of students, not yet so firmly ingrained in the Newtonian mindset, could grasp the new relativity when their teachers expounded it. In this short series of papers 1, 2 I will roughly outline where the founders of mechanics and electromagnetics went wrong, and indicate the way to correct the fundamental errors. In addition, I will briefly point out some of the implications, and speak of some direct experimental proof. Bearden, T.E. Comments on the new Tesla electromagnetics, Part I, Discrepancies in the present M-theory, Part 2, The Secret of Electrical Free Energy, Tesla Book Company, 1580 Magnolia Avenue, Millbrae, California 94030, 1982. Bearden, T.E. Solutions to Tesla Secrets and the Soviet Tesla Weapons, Tesla Book Co., 1981. Also Ratzlaff, John T. Reference articles for Solutions to Tesla Secrets, Tesla Book Co., 1982. Note we are applying the rule, a thing is that which it does, and it does that which it is. Actually this is one statement of a fourth fundamental law of logic not incorporated by Aristotle. See Bearden, A Conditional Criterion for Identity, leading to a fourth law of logic, DTIS report, available through the National Technical Information System, Port Royal Road, Springfield, Virginia 22161. Specifically, the resulting theory becomes a curtailed, special case of the much more fundamental electrodynamics and electromagnetics that actually exist. We point out here that measuring a field of force existing in the electron gas in a probe of the measuring instrument is not at all the same thing as measuring a force in the vacuum, nor does it establish that a force exists in vacuum. Indeed, it is already well known that the field concept itself will not withstand rigorous logical examination. For a discussion rather clearly showing the present difficulty in defining a field, see Robert Bruce Lindsay and Henry Marginaw, Foundations of Physics, Dover Publications, New York, 1963, pages 283 to 287. Note particularly on p. 283 that a field of force at any point is actually defined only for the case when a unit mass is present at that point. It is then illogically assumed that the force continues to exist at the point in the absence of the mass, which of course need not follow at all. On p. 284, note the similar logical paradox connected with the idea of a scalar gravitational potential field. The potential field is only defined at a point when mass is present at that point, and it is specifically defined as the potential energy per unit mass for a particle present at that point. If there is no mass present, neither a force vector field nor a scalar potential field is defined there. Assignment of these fields to the point in the absence of the mass is an assumption, not at all a definition. Since a true definition is an identity, then the entity identified, defined, to include the presence of mass is not identical to the entity resulting when that mass is absented. To see just how arbitrary and postulational are present definitions of mass and force, see Lindsay and Margina, Opus Citation, pages 84 to 101. Also see Richard P. Feynman, Robert B. Layton, and Matthew Sands, The Feynman Lectures on Physics, Addison Wesley, New York, Vol. 1. 1963, 4th printing July 1966, p. 4 for a definition of the electric field in the context of its potentiality for producing a force. Again, the force only exists when a particle of mass is present. From these examples, one can see the implication that a physical field is something such that, when a mass is introduced into it, the mass exhibits an effect. For a force field, this is tantamount to stating that there exists some mechanism connected with a field which, in the presence of a mass, causes a force to be exhibited. In that case the force is an effect, not a cause, and there is a more fundamental mechanism that generates force itself. See also field discussions in Feynman, Richard, The Character of Physical Law, MIT Press, Cambridge, Ma, March 1967, 2nd printing September 1967, Passim. While in Europe prior to 1881, Albert Abraham Michelson performed his first interferometer experiments to determine the velocity of the Earth through the ether, obtaining essentially null results. At the Case School of Applied Science in Cleveland, Ohio, he perfected his interferometer experiment from 1883 to 1887, assisted by a colleague, chemist Edward Williams Morley. By 1887 the results were ready and announced. Michelson himself thought his experiment had proven Stokes' theory of an ether dragged along by the Earth in motion, and thus motionless with respect to the Earth. This was at odds, however, with certain other experiments indicating a moving ether. The Michelson-Morley experiment was finally reconciled with these other experiments by Fitzgerald's suggestion in 1892 that the physical dimensions of material bodies are altered when they are in motion. In 1907 Michelson was awarded the Nobel Prize, the first American to receive it in the sciences. See Lindsay and Margina, Foundations of Physics, 1963, pages 324 to 326, D. C. Miller, The Ether Drift Experiment and the Determination of the Absolute Motion of the Earth, Reviews of Modern Physics, Volume 5, p. 203, 1933. Actually the experiments did not yield a conclusively null result, but rather showed large systematic trends. For a typical elimination of the systematic trends, see Hanshi, M.A. Re-examination of the 1887 Michelson-Morley experiment, American Journal of Physics, Volume 50, Number 11, November 1982, pages 987 to 990. See Rho Sigma, Ether Technology, CSA Printing and Bindery, Lakemont, Georgia, 30552, 1977. For several enlightening points on the vacuum ether, see A. K. Lapkovsky, Relativistic Kinematic Equations and the Theory of Continuous Media, Soviet Physics Journal, Volume 21. Number 6, June 1978 for an abstract describing Soviet utilization of the concept of a small particle, called by Bearden a Quitton, in Quitton/perceptron physics, DTIS, 1973, of the medium. See Believ, B.N. On random fluctuations of the velocity of light in vacuum, A Zvesti Yavishchik Uchebnik Zavdani, Fizika, Number 11, November 1980, pages 37 to 42, translation by Plenum, for discussion of the proven variation of the speed of light in vacuum. The velocity of light in a vacuum on Earth is measured to be higher than the velocity of light in the vacuum of deep space. See Graham, G.M. and Lahaz, D.G. Observation of Static Electromagnetic Angular Momentum in Vacuo, Nature, Volume 285, May 15, 1980, pages 154 to 155 for the first direct observation of free electromagnetic angular momentum in vacuum. C. Davies, Paul, Something for Nothing, New Scientist, May 27, 1982, pages 580, 582 for a discussion showing that modern theories of the vacuum reveal that even empty space is seething with activity. An ether of sorts emerges from vacuum fluctuations due to quantum mechanics considerations. C. Hooper, William J. All-Electric Motional Electric Field Generator, U.S. Patent Number 3610971, October 5, 1971 for a generator which produces a gravitational or inertial field. Einstein suggested that vacuum, complete with electromagnetic and gravitational fields, be called the ether. Dirac certainly did not abandon an ether, for in 1954 he stated the etherless basis of physical theory may have reached the end of its capabilities and we see in the ether a new hope for the future. James Clerk Maxwell derived his famous equations based on an ether theory. Sir Arthur Eddington also believed firmly in an ether. Sir Oliver Lodge actually pointed out the dilemma which yields the approach in this paper, writing of the ether in his book, The Ether of Space, Harper and Brothers, New York, 1909, he stated, "We have no means of getting hold of the ether mechanically, we cannot grip it or move it in the ordinary way, we can only get it electrically. We are straining the ether when we charge a body with electricity, it tries to recover, it has the power of recoil." But when electrical theory was being founded, scientists thought of space as something rather fixed, and filled with a thin material ether. They did not realize that space itself does not exist except after an observation. Before the observation, space-time exists, indefinite in both length and time. They did not know that electrostatic scalar potential in fact was space-time, hence also the vacuum and the ether. In assuming that the charge of vacuum is zero and that charge and charged mass are identical, they hid the answer to the dilemma and placed the foundations of electromagnetics on its present unsound basis. The field, of course, is indeed a highly useful concept and this author certainly does not recommend its abandonment. Instead, he recommends that it be placed on a sounder logical basis. Specifically, they came to feel that the electric field which was improperly defined, was what was waving. In fact, Einstein once proposed that the vacuum, complete with its electromagnetic and gravitational fields, should be called the ether. His proposal was not adopted. C. Born, Max, Einstein's Theory of Relativity, Revised Edition, Dover Publications, New York, 1965, p. 224. Particularly from the work of Schrödinger, Born, Dirac and others. For example, see Lindsay and Marge. Now, Opus Citation, pages 287 to 288. A physical vector is thought to be defined by its magnitude, its direction in space, and its transformation characteristics. Actually, that is a geometrical vector, not a physical vector. It does not tell us what a vector consists of, but only tells us some of its important characteristics. Remember that a true definition must be an identity. Here a reading of Lindsay and Margina, Opus Citation, pages 79 to 81 may prove enlightening. Also note that velocity, or L/t considered at an instant, stopped, represents an idea of motionless motion and is an application of the fourth law of logic. For a discussion of the fourth law of logic and its usage, see Bearden, Thomas E. A conditional criterion for identity, leading to a fourth law of logic, Specula, Journal of the AAMS, P.O. Box 1182, Huntsville, Alabama 35807, Combined Volume 3, No. 4/Volume 4, Number 3, October 1980 to March 1981, pages 50 to 57, also available from Defense Technical Information Service. Note this is an identity of opposites, which explicitly violates the three Aristotelian laws of logic. See Bearden, A conditional criterion for identity, leading to a fourth law of logic, Locative Citation, 1981. Again note the fourth law of logic, zero motion, the absence of motion, being recognized as a special case of the presence of motion. Also, physical reality consists of internested levels, and any physical object has an internal substructure of nested levels of finer structure, extending down into the virtual, non-observed, state. For a vector to model, apply to, a physical object, it itself must be modeled in such fashion as to reflect this kind of substructure. Thus the use of geometrical vectors as models of physical objects in motion is presently flawed in a fundamental fashion. The reader is most strongly urged to read Morris Klein, Mathematics, The Loss of Certainty, Oxford University Press, New York, 1980 as a prelude to understanding what mathematics is and is not, and what it does and does not. Refer to Lindsay and Margina, Opus Citation, pages 79 to 81 to see how the ideas of motion and vector are inextricably entangled with the idea of a particle. Call it uncertainty or call it constituency, a quantum change is composed of two canonical entities inextricably welded together into a single entity. Time is an unavoidable, non-exclusive constituency of the welded quantum. Simply from the definition of force as consisting of a time and length smeared mass motion change. The force is an effect, not a cause. It is the smeared charged particle. It is caused by a more fundamental mechanism. It is the result of the combination of 1. A non-zero delphi, and 2. The presence of a spinning charged particle. In a delphi, the spinning charged particle accelerates itself. This is the fundamental secret of free energy that was suppressed, to bury the fundamental work of Nikola Tesla, shortly after Tesla was forced to abort his Wardenclyffe attempt to provide the world with free energy. To quote, the Hertz wave theory of wireless transmission may be kept up for a while, but I do not hesitate to say that in a short time it will be recognized as one of the most remarkable and inexplicable aberrations of the scientific mind which has ever been recorded in history. Nikola Tesla, the true wireless, electrical experimenter, May 1919, p. 87. Note the Soviet scientist Kozyrev's experiments with time waves. See Kozyrev, N.A. Possibility of experimental study of the properties of time, September 1967, pages 1 to 49, in JPRS 45238, May 1968. Kozyrev reports real physical effects from the oscillation of time. Also, note that scalar potential energy of appreciable size with respect to a particle's rest energy can force the situation to be relativistic, even though the velocity of the particle with respect to the velocity of light is small. That is, electrostatic scalar potential alone can cause variation in the rate of flow of time and hence very physical characteristics. See Bloch and Crater, Lorentz invariant potentials and the non-relativistic limit, American Journal of Physics, Volume 49, Number 1, 1981, pages 67 to 75. By inference, oscillating the electrostatic scalar potential can produce time waves and lead to direct physical effects. It is already shown in the literature that the electrostatic scalar potential, ESP, can affect spacetime, ST, in the same manner as velocity. Cf. Bloch and Crater, Opus Citation, 1981. Now note that, to any quantal or macroscopic observer, the existence of the four-space volume of spacetime implicit in T, V, where V is volume, cannot be separated from the existence of the subquantal entities that exist therein. We therefore define the magnitude of the electrostatic potential as the summation of the absolute values of all the internal virtual vectors in the T, V, quantum of spacetime, divided by the absolute value, magnitude, of T, V. We take the view that no such thing as unstressed spacetime physically exists, and that spacetime and stressed spacetime are identical. Hence electrostatic potential and spacetime are one and the same thing. Note that this implies that the virtual density of spacetime is variable, and is nothing but the magnitude of the electrostatic potential. In M-theory, the assumption that the electrostatic potential of vacuum, O, is equal to zero is in serious error. In fact, O is spacetime of the laboratory observer, in the new view. For example, the definition of the electrostatic potential, ESP, is usually taken as the work which must be done against electric forces to bring a unit charge from a reference point to the point in question. The reference point is located at an infinite distance, or, for practical purposes, at the surface of the Earth or some other large conductor. McGraw-Hill Dictionary of Scientific and Technical Terms, ed. Daniel N. Lapides, 2nd edition, 1978, p. 518. Note that this is not a definition at all, for it is not an identity. Instead, it is the statement that, if an electrostatic potential exists at a point and a unit charged mass, assumed to be at a point, is brought in from infinity toward the electrostatic potential location point, the amount of work it is necessary to expend upon the mass of the particle is equal to the magnitude of the electrostatic potential. The electrostatic potential exists whether or not any work at all is expended, and whether or not a charged unit mass is brought in. To adequately define electrostatic potential, we must define its identity, or what it consists of, in the absence of mass, since we have conceived the electrostatic potential to exist at a vacuum point. Further, the definition usually taken is completely a three-space definition. Instead, in our new view, the electrostatic potential is to be taken at a point in n space, where n is equal to or greater than 4. See Bearden, Quitton/Perceptron Physics, 1973. Available through the DTIS. See also Bearden, The Excalibur Briefing, Strawberry Hill Press, San Francisco, CA, 1980. Ultimately, all physical phenomena are mind changes in the minds of all the observers. It started with geometry and grew. At the very beginning of what we call the scientific period, mathematics was both king and queen, and Euclidean geometry was its handmaiden. So we ask, what precisely is geometry? Here we are not interested in a textbook answer, but in an answer indicating what geometry really does. In other words, with what does geometry concern itself, and what is the fundamental nature of those things with which it concerns itself? Briefly, geometry, at its foundation, is totally spatial. It is fitted to, and expressed in terms of, the total absence of mass. Thus the geometer deals in abstract, massless entities called points, lines, planes, etc. When the geometer speaks of motion, he speaks of a time-smeared, length-smeared point. Geometry at heart is massless, and a geometer's vector is a highly specific type of system. In fact, it represents the time-smearing and length-smearing of a point. A priori, the fundamental concept of the geometrical vector has taken a spatial entity and introduced a hidden involvement with time. Modern mathematics and physics have followed an intertwined development for several hundred years, and both sprang as offshoots of the original work of the geometers. Let us briefly sketch the overall path of interest taken by these two developing disciplines. With the advent of Descartes' fundamental work, algebra was combined with geometry to yield analytic geometry, a new and powerful mathematical tool. With the invention of calculus by Leibniz and Newton, both mathematics and physics received a giant impetus. Differential geometry and vector mathematics arose in full splendor and, in physics, mechanics leaped to the forefront with Newton's profound work. But the mechanics made a most fundamental error when they simply applied the geometer's vector to a mass, to produce, so they thought, a mass vector. That which rigorously applies only to the absence of mass cannot be so lightly applied to the presence of mass without the risk of serious limitations in the resulting theory. The precise difference between a geometer's massless vector and a mechanic's mass vector is one of the issues to be developed in this thesis. As rapid development continued in mechanics and mathematics, certain physicists were involved in intense experimental work on charged matter, becoming the first electricians. Both the preceding mathematical ideas and constructs as well as the preceding, partially erroneous, mechanics constructs and ideas were applied by the electricians, struggling with their pith balls, cat fur, and glass rods to understand, quantify, and model electrical forces and the phenomena of charged matter. In other words, the electricians strove to formulate the physics and dynamics of charged matter and its interactions by simply adding to the work of the geometers and mechanics. Here again, a fundamental logical error was made. That, geometry, which a priori applies only to the absence of mass, and that, mechanics, which a priori applies only to the absence of charge, cannot be lightly applied to the presence of charged mass, both mass and charge, without risking the incorporation of grave limitations in the resulting theory. After the profound work of Maxwell, the idea of fields of force became more prominent, until the field concept ruled the day. The electricians continued, pushing the idea of fields into space and vacuum itself, along the way inventing the idea of charge effects existing even in the massless vacuum, with concomitant fields. Meanwhile, they had thoroughly confused chargeless point smeared, chargeless mass smeared, length smeared and time smeared vectors. After a set of fundamental experiments designed to detect motion of the material ether yielded essentially null results, 6, Michelson and Morley were regarded as having completely disposed of the ether, even though the experiments only disposed of material ethers, and not Lorentz invariant non-material ethers. Maxwell's equations and the field concept were elevated to profound importance. Then, after Einstein's fundamental relativity work shortly after the turn of the century, the ether concept faded away and the field concept reigned supreme. Indeed, in their enthusiasm the interpreters of relativity went so far as to affirm that one can have a wave without any medium, that is, that something can be moving, waving, without anything there to move. 9 And with great glee they pronounced the final end to the idea of ether as a medium, even though Einstein himself never did any such thing. 10 With the advent of Einstein's general theory of relativity, even matter came to be regarded as just a special kink or curvature in space-time or vacuum. Nothing. Quantum mechanics arose and even certainty and determination fell. Chaos, probability, and randomness now assumed the ruling position. Probability waves, and probability fields, arose, 11, as did quantum fields of various kinds. The intermingling of these concepts with the concepts of electrodynamics pushed the idea of the field even farther into esoteric realms. The point is, each of these developing disciplines incorporated and built on the foregoing disciplines. From the beginning of geometry, there was no rigorous definition of a vector, and there is none today. From the beginning of mechanics, in their foundations the theorists made grave logical errors by incorporating the geometer's vector, errors so great that today mechanics and electromagnetics are severely flawed, as is everything that came after them and built upon their illogical foundations. Points and motion. It is my purpose in this paper to expose in a very simple fashion the most basic errors that were made. One basic error involves the idea of motion itself. In formulating concepts of motion, the geometers used a point in motion to determine or specify, for example, velocity. Now a point is a static concept a priori. To determine, or even to think and perceive, motion, one must determine that it occupies two different points, positions or locations, at two different times, yet consider both points at the same time. Indeed, that is precisely what the arrow means that is used to represent a vector. A point in motion therefore represents a contradiction of opposites. That is, it represents the idea that that which is motionless has motion. Even with this, there is a difference in a spatial point and a spatiotemporal, spacetime, point. To exist at all, a spatial point must be moving in time, in other words, it is a spatiotemporal line, even if it is a static spatial point. Vector analysis was constructed in the abstract. Again, a massless point in motion possessed or constituted a velocity vector, etc. In massless, and timeless, space, fields were defined. Scalar fields constituted the assignment of a simple motionless number, magnitude, to each spatial point, while vector fields constituted the assignment of a simple vector, magnitude and velocity, to each spatial point. But the mathematical vector system consisted of massless, point, motional relationships, recognizing zero motion as a special case of motion. 15 Of course, mathematics development was also always intertwined with practical problems. With the sustained application of mathematics to gross physical material problems, mechanics slowly arose. These developments required decades and even centuries to occur completely. All along the way, innovations and changes, and additions to the mathematical formalism were being derived and taught to students as the natural system of reality. A permanent mindset was being forged. Indeed, mathematics was regarded as the single human expression of fundamental truth. Not until Gödel's work in the 20th century did it become evident that mathematics is simply a game played according to assigned rules, and there is no ultimate truth in mathematics alone. 16 It is a most useful game, of course, since it is the game fitted to perception. Thus it applies, essentially, to whatever can be perceived. But to be applied to physical systems, it must be changed, altered, updated, and fitted as the perceiving/detecting instruments become ever more subtle. 4 types of vectors actually emerged. As the physical sciences slowly developed and incorporated abstract geometry and mathematics, in actuality 4 major types of vectors and 2 major states of observation evolved, although this fact did not become apparent to the scientists. Specifically, the mathematicians and scientists failed to recognize the differences in the 4 types of vectors, hopelessly intermingling them and confusing them as a single class of vector. Further, they did not appreciate that a fundamental vector conceptually is a unitary system, and the system represented by one of these 4 types of vectors utilizes and is comprised of different components, welded together with no seam in the middle. Conceptually, and from a system's viewpoint, the 4 types of vectors are: 1. The chargeless, massless spatial system vector, geometers vector; 2. The uncharged mass system vector, mechanics vector; 3. The charged mass system vector, electricians vector; and 4. The charged space system vector, advanced electricians vector. These 4 fundamentally different vectors are shown in figures 1, 2, 4, and 9 in a simplified manner. The major problem was that, beginning with the geometers vector, these 4 major types of vectors were not treated as systems. Instead, their vector aspects were hopelessly confused and intermeshed, and no distinctions were made between them. And in the foundations of the mathematical constructs, time smearing was not recognized at all. Quantum mechanics compounds the problem. In addition, the 2 presently recognized observation states, observable and non-observable, virtual, were of course unknown to the early geometers and electricians, and these ideas were not incorporated directly into the theoretical foundation. From particle physics and quantum mechanics, we now understand that physical reality is structured of an observable state, underlaid with an infinite number of ever finer, successive levels of virtual, unobservable, states. At least reality is most accurately modeled in that fashion, according to particle physics today. It is also well known, for example, that at the most fundamental level, one cannot actually separate non-motion from motion, which implies, for example, that one cannot separate mass and velocity. In other words, a mass in motion idea is actually incorrect, at the most basic level. What actually exists is a sort of smeared mass. That is, mass motion is fundamentally what exists, not mass in motion. Actually, all that the Heisenberg uncertainty principle implies is this fact: if one examines the concept of static, non-smeared, thing in non-static, smeared, motion, in ever finer detail, one reaches a degree of fineness where the smearing is paramount and one cannot have an unsmeared or separate static thing to be in motion. Instead, one only has the smeared, 4-dimensional space-time entity, without 3-dimensional spatial separations. This means, for example, that at the most basic level, it is actually incorrect to represent a momentum with a little static particle of mass connected to a spatial velocity vector. It is incorrect to think of the system as comprised of 2 separate entities, 1, a mass, and 2. A massless spatial system velocity vector, a geometers vector. We mention in passing that, presently, we understand that every particle is continually accelerating. First, the particle has spin, which involves rotation, which means that every part of the periphery of the particle is accelerated toward the center axis of spin. Second, every particle is continuously fluctuating, and these fluctuations are accelerations. Further, we must consider any change such as an acceleration, as existing in a small time increment, and occurring in a small length increment. Thus mass particles actually exist as mass x acceleration x time x length. This of course has the dimensions of action or angular momentum. The real world of physical matter, then, is composed of building blocks of action, called quanta. Any other physical quantity must be obtained by fissioning, differentiating, the action quantum. For this reason, quantum mechanics presently must postulate that to every observable there corresponds an operator. To summarize briefly, let us now summarize these concepts and further examine their impact. In physics, there must actually exist four major kinds of vectors, rather than just one as prescribed by present interpretation. These vectors are built. Starting with four major kinds of particles 17, these are, 1. The spatial point, 2. An uncharged mass particle, 3. A charged mass particle, and 4. A charged spatial point. Further, each of the four vectors at its most fundamental level, that is, at the quantum level, 18 is actually an inseparable, unitary system welded into a single undivided entity containing time and existing non-exclusively in time. 19 When we look at or represent the so-called parts of the system, we are looking at them before they are welded together into the physical vector. That is, whenever we speak of parts, we imply that a cutting or differentiating action has been implied to separate the system into such parts. From such considerations, four different kinds of system vectors result. Geometers vector. Figure 1. Uncharged spatial, massless, system vector. Uncharged spatial, massless, system vector. This is the geometers abstract vector, consisting of a point in motion. Actually, it is a smeared point, for example. However, so ingrained is the concept of a point in motion velocity vector that we now consider it to be natural because of its total familiarity. But simply ask, what is in motion 17? And you immediately see the difficulty. To have a what, one must stop the action, detect or measure, separating static from non-static. Acceleration and other vectors, etc. have also been derived by the geometer and utilized in similar fashion. All are massless. Mechanics vector. Figure 2. Chargeless mass system vector. Chargeless mass system vector. This type of vector actually is the essential vector of mechanics, involving mass motion, momentum, force, mass motion change, etc. The fundamental difference between this type of vector and the geometers vector is the presence of smeared mass existing in time, i.e., mass time, welded together with a geometers vector, but with no seam in the middle, into a new kind of vector as a system. The vector is the system existing in time. To illustrate, momentum is more properly referred to as mass motion rather than mass in motion. That is, at the fundamental level, the mass is not separate from its motion. It is not separated from the time in which the smearing occurs. The idea of momentum, however, is really to express the time density of the mass smeared through length. It is, in other words, the time rate of length smearing of mass. Now in our minds we have conceived that where, by the symbol we mean coupled to, but we actually have. Where we are not allowed to separate, even in thought, m and. Quantum mechanics agrees with this essentially, because is a canonical variable linked to length, in any observable physical change. The reason p is canonically linked to L is because is the time rate of length smearing of m. If there is no length, there is no length smearing of m to have a time rate of in the first place. Note that, not only is, but also, which is a much stronger and quite different statement. That is, pulse is identically mass times velocity, not just calculably equal to m. This means that is a system that is comprised of mass motion. What force is? We now note that force, for example, is, and may be defined as, the time rate of change of momentum, or force equals rate of change of magnitude of impulse. And this identity states that a force, any force, is comprised of time-changing mass motion. As such, the force vector is a mass system vector, not just a massless spatial vector. Fundamentally, this mass system vector is a totally different creature from a massless spatial vector. Our present manner of considering force as a geometer's vector separately applied to a mass particle is completely erroneous at the quantum level. Instead, fundamentally force is always a mechanics vector. Force is an effect, not a cause. And here mechanics made a most fundamental error, in not recognizing the difference between its kind of vector and that of the geometer. Force and Hertzian waves cannot exist in vacuum. Note that one cannot have an observable force vector existing in vacuum a priori. For example, we have the definition of force as or. And we see that, rigorously, a force vector consists of, not, is equal to, a time-changing mass motion vector system. If there is no observable accelerating mass present, then there can be no observable force present. The mass can accelerate in time, increase or decrease of mass, or space, increase or decrease of velocity, or both. Observable force cannot exist in vacuum, in the absence of mass, a priori. However, assume for a moment that one could have a massless force vector, as assumed in present electrical theory. Let this force vector appear at a point in the vacuum. Since the vacuum has zero observable mass, it would have zero inertial resistance to this hypothetical observable force, hence the observable force would instantly produce an infinite acceleration of its point of application, vanishing with it into the infinite distance. Therefore our fictitious force would disappear the instant it appeared. In any case, it could not be retained at a point in the vacuum for any finite length of time, however small. The direct implications are that, 1. Something other than an observable electrical force field exists in the vacuum, and, 2. There must exist a more fundamental mechanism by which the something else generates or creates a force on slash of a moving electrically charged mass. Note again that, at the most basic level, any particle of mass is always quivering, in motion, and accelerating from quantal considerations alone. Thus immediately we have discovered something unique about so-called force fields in vacuum, for example, about gravitational field, electrical field, and magnetic field, and the strong force and the weak force as well. These fields do not exist at all as ordinary force vectors, and real force fields, in vacuum. E and B fields, for example, are defined in terms of force per unit electrical charged mass and magnetically charged mass, respectively. In the absence of mass, they cannot exist. And this in turn means that transverse H-field waves, Hertzian waves, cannot exist in a vacuum. Indeed, they appear on, and are constituted of, the charged mass motion that changes, and they appear where such change occurs, as a result of an introduced mass. But in the absence of the spinning charged particle of mass, they do not exist as force fields at all. Hertzian waves exist in a transmitting whip antenna, for example, in the oscillating electron gas along its length. Something else entirely different exists in vacuum between the transmitting antenna and the receiving antenna. Then in the receiving antenna, Hertzian waves again exist in the oscillating electron gas along its length. See Figure 3. Normal electromagnetic wave, normal transmitter, transverse electromagnetic wave, transverse oscillations induced in electron gas. Detection. Normal electromagnetic wave, scalar transducer, longitudinal wave, special antenna, special detector. This is interesting, For Nikola Tesla stated several times that Hertzian waves cannot be produced in a vacuum, nor can they travel in a vacuum. Tesla was correct, as we are beginning to see. We shall later return to show in what form so-called force fields actually exist in vacuum. For now, I point out that I am stating a fundamental change to all of physics, including both mechanics and electromagnetics. Electrician's vector. Figure 4. Charged mass system vector. Charged mass system vector. Figure 4. The third type of vector we meet is the vector mass system where the mass is charged. First, we point out a serious error in present electromagnetic theory. That is, in present theory it is implicitly assumed that charge equals charged mass. In other words, charge and charged mass are erroneously assumed to be identically the same thing. In the days when electricians were playing with pith balls and striving to uncover the secrets of electricity, they knew nothing at all about the virtual state, and consequently nothing about a virtual particle flux on a particle of mass causing, and comprising, the charge of that mass. Today, of course, we know from particle physics and quantum mechanics that the charge on an observable particle of mass is due to a flux of virtual, non-observable, particles on and off the mass of the observable particle, see figure 5. A charged mass is thus presently known to be a system, a massless charge flux, coupled to a bare particle, chargeless mass, constitutes a charged particle. Figure 5. The charge on an electron mass consists of a flux of virtual particles on and off the mass. Thus, actually the charge is the virtual, unobservable, or spatiotemporal, flux to and from the observable spatial particle of mass. So, rigorously, charge doesn't equal charged mass, but instead. And this is a definition and therefore an identity. This definition alone affects all present electromagnetics theory. To illustrate, in founding electrical theory, early scientists dealt with forces generated by charged masses, for example, charged pith balls. They later extrapolated the experimental results they obtained, or thought they obtained, with the smallest charged mass, a charged particle. In figure 6, I show the classic situation for derivation of the idea of E-field, except we have used an electron for our test charge, rather than a pith ball. Fixed static charge. A negatively charged test mass, QM2, for example, an electron, brought into the vicinity of a fixed charged mass QM1 experiences an acceleration as shown. At the quantum level, the smeared electron cannot be separated from the smearing. And it becomes charged mass motion changing vector. Figure 6. A test charge, charged mass, brought near a fixed charge, charged mass, experiences an acceleration. Now note that what actually happens is that the unrestrained test charge becomes a charged mass system vector, a smeared charged mass motion changing. The test charge becomes a charged mass force vector, it does not have a separate geometers vector appear on it. What actually happens is shown in figure 7. A charged mass system vector. That is, in the simplest, non-relativistic, case, for an electron what happens is. And this is a definition. That is, considered instantly, the electron exists as a charged mass electrical force consisting of / comprised of a charge flux QE canonically coupled to a mass, with that subsystem then canonically coupled to a spatial acceleration vector, all as a single entity, without any seams between its parts. The centimeter is the electron system itself, it is not a spatial vector. Rigorously, it does not exist in the absence of the smeared electron mass, a priori. Again, in assuming this force exists in the absence of the smeared mass of the moving particle, electromagnetics theory is in serious logical error. Referring back to figure 6, we see that, if we repeat the experiment many times and with the test charge in many locations, we have the situation shown in figure 8. Figure 8. Repeating the test charge experiment. It is found that, rigorously, where force centimeter is a charged mass system vector, Erroneously, this has been stated one way or another as where force is assumed to be a spatial system vector. Further, this confusion has been carried over into the definition of the field as. In this definition, E, which is a charged mass system vector, has been confused as a charged spatial system vector, where F is regarded simply a spatial system vector. Actually, the definition of the E field should be where F centimeter is a charged mass system vector. Failure to properly define the E field has caused the conception of the E field to be falsely perpetuated as existing in vacuum. The E field is treated this way in present M theory. Hence present theory falsely assumes that the observable E field can exist in vacuum. What actually exists in space, E field-wise, is a special kind of ordered virtual state pattern in a series of spinning scalar fields. This virtual state pattern or shadow vector field will be explained later. Note again that one cannot have a force vector existing in vacuum, a priori. However, assume for a moment that one could have a massless force vector, as presently assumed. Let this force vector appear at a point in the vacuum. Since the vacuum has zero observable mass, it would have zero inertial resistance to this hypothetical observable force, hence the observable force would instantly produce an infinite acceleration of its point of application, vanishing with it into the distance. Therefore our fictitious force would disappear the instant it appeared. In any case, it could not be retained at a point in the vacuum for any finite length of time, however small. The direct implications are that, 1. Something other than an observable electrical force field exists in the vacuum, and, 2. There must exist a more fundamental mechanism by which the something else generates or creates a change on / of an accelerating electrically charged mass particle. Note again that at the basic level, any particle of mass is always quivering and accelerating, from quantal fluctuation considerations alone. Causality has no arrow microscopically. Advanced electrician's vector. Figure 9. Charged spatial, massless, vector. Charged spatial, massless, vector. We recognize now that charge is not equal to charged mass, and that QC is simply the virtual particle flux that constitutes charge, and indeed constitutes vacuum itself. We define vacuum, based on figure 5, as shown in figure 10. There is no emptiness filled with charge. Rather, there is massless charge, from which emptiness is constructed, and from which space-time is constructed, and from which mass and motion are constructed. Figure 10. Removing the bare particle, mass, from a charged particle leaves the charge. The vacuum is defined as the charge. That is, vacuum may be defined as pure massless charge flux. This flux is identically space-time as well. Vacuum is pure field, electrostatic scalar potential. Here again, in present theory it is assumed that, which, by our new definition of vacuum, is quite false. We now note that, if we insist on assigning a spatial vector to the vacuum, we have the situation shown in figure 11. Figure 11. Assigning a spatial vector to the charged vacuum. The shadow vector. Note that this spatial vector represents dielectric permittivity, that is. But dielectric permittivity cannot be a force, mass system, vector. It can only exist as an ordered pattern in the virtual flux between two separated points of the vacuum, that is, as an ordered pattern in the virtual state. Literally, exists only as a tiny bit of order existing in great disorder. In other words, the present M theory is incorrect in stating that electric field equals gradient of electric charge. In vacuum, in the absence of an observable spinning charged particle, since the actual existence of may be visualized in terms of successive differentials of, broken into differentials so small that, observably, each little differential's mass component m has become virtual, so that, where subscript m stands for mass, subscript v for virtual, and observably. But, in the absence of a spinning charged particle, since the components remain individually separated, that is, in macro time a shadow force vector exists, made of microscopically ordered but unjoined, unintegrated, virtual state vector differentials of what would be an observable mass system force vector if integrated. Thus, the E vector that exists in vacuum is a shadow vector as shown in Figure 12. Figure 12. A shadow vector. We say that such a previous mass system vector, broken into ordered but unjoined virtual vectors by the absenteeing of all mass, is a shadow vector, and we label it with a subscript Vm, to represent virtual mass system. To the macro observer, this is the kind of vector that exists in vacuum. Note that, observably, the shadow vector merely represents a special ordering in. It is not an observable, mass system, vector, but it is an ordered series of consecutive virtual vectors. With each virtual bit vector, a virtual time exists as well, and these virtual time bits are also ordered consecutively, in macro time. I point out that any observable vector must be finite, and so it must have a finite magnitude, finite length. In the simplest case, this length L is related to a bi. What I am saying is that any observable spatial vector is actually a spatiotemporal vector, and the magnitude of any vector is related to time, to the existence of that vector in time, at the most fundamental level. Suffice it to say that, if the fundamental quantum level, t, aspect of a vector is interfered with, then the magnitude of the vector is interfered with. That is, if we can make a time wave, we can change or affect any vector's magnitude, including the magnitude of mass system vectors and charged mass system vectors. Such a time wave can be made easily, and it has been. A scalar is a zero vector. Now let us look at the idea of a scalar. A scalar may in a general sense be considered as the sum of the absolute values of the individual vector components of a system of vectors whose observable resultant is zero. That is, it represents the magnitude of the internal stress of a vector system, with the absence of a single observable directionality of the system. It also follows that every scalar is actually a stressed zero vector, and every zero vector is a scalar. Thus we have four major types of scalars related to the four types of vectors. Where S stands for scalar, for vector, and subscript S for spatial, M for mass, and C for charged. For example, comparing equations 25 and 26, it can easily be seen that twice as many point motions is not at all the same thing as twice as many gram mass motions. The two resulting vector systems are quite different. Virtual and observable aspects. We must also examine some aspects of virtual and observable. For example, we construct several spatial vector summations in Figure 13. The resultants of these spatial vectors are all equal. However, the actual sums, even though equal, are quite different, because their internal stresses, substructure forms, are quite different. Superposition does not eliminate the virtual substructure. When the time aspects of the vector systems of Figure 13 are considered, one can easily understand the problem. That is, the resultant of each of these systems is zero, and so one can say that the vectorial magnitude of the system is zero since the magnitude of the resultant vector is zero. However, in each case the action represented by each vector element actually occurs in a finite tiny t. So, 1, the zero resultant must exist for a finite, and, 2, all the actions indicated by the system component vectors actually occur in that t. The absolute value of the activity per unit time per unit volume of such a zero resultant system thus has physical meaning, and one may refer to this notion as the stress on spacetime, or the electrostatic scalar potential of the system. Note that this differs from the present definition of electrostatic scalar potential, which becomes just a special case of the more fundamental potential defined here. The derivatives of this spatiotemporal stress also have physical meaning. The time derivative is indicative of the stress on the flow of macroscopic time at a fixed spatial point, and the spatial derivative is indicative of the stress on space. Here one is confronted with the fact that what we call space and time are continually being created, directly in the physical observing/detecting apparatus itself. That is, rigorously, detected physical reality exists totally in and of the mass changes of the observer's mass or his detecting instruments. In the fundamental detection process itself, there is a flow of the rate of creation of spatial lengths and a flow of the rate of creation of time lengths. Indeed, to a linear observer the stress on the creation of the flow of time controls the flow of the creation of space, and the stress on the creation of the flow of space controls the flow of the creation of time. The change in the stress on 4 space, ordinary Minkowskian spacetime, controls the curvature of that spacetime in the 5th dimension. The change in the stress on 5 space controls the curvature of that 5 space spacetime in 6 space, and so on. Development of these facets of the new concepts is beyond the scope of this paper. Scalars and vectors have substructures. As can now be seen, the sum of each structure in figure is observably zero. Therefore we might define the sum as a zero spatial vector. We note, however, that it actually exists for a time t and is thus a spatiotemporal entity, rigorously. If we define the internal stress action A in a region of space-time as and the 4-space internal stress intensity or potential as, where is any internal vector in the substructure, is the spatial volume, about a point, containing vector, and is the inseparable time during which these component actions occurred, then we see that, stress-wise, all the zero vectors in figure 13 are quite different in their internal stresses, 4-space potentials, and internal substructures. For the 5 zero-sum vectors, observably we have whether or not. But considering the substructures, I now point out that a scalar can be regarded as a stressed zero-sum vector, where the magnitude S of the scalar represents the internal stress intensity caused by the substructure of the zero vector. Thus, generally, that is, in general any observable scalar has, consists of, and is comprised of a virtual, unobservable, substructure that is very real indeed. One must also consider the scalar as existing for some finite time t, at least for the time of one quantum change, and the intensity of the virtual actions occurring in the spatiotemporal substructure of the scalar during that time t is proportional to the magnitude of the scalar. Normally, the concept of a scalar, as presently used, makes no allowance for the scalar to exist in time, or for a virtual vector substructure, or for any patterning inside the substructure. This is equivalent to assuming that, and that all S are evenly distributed. That is, from this new viewpoint, presently the mathematical theory assumes all scalars to have an equal density of virtual activity per spatiotemporal volume in its virtual substructure, and an isotropic virtual pattern distribution of an infinite number of equal virtual vectors in its 4-space substructure. In the new approach, neither of these two assumptions need hold, though in special cases they can hold. Thus present orthodox theory is just a single special case of a more fundamental approach indicated here. Note that, by directly affecting and changing the virtual substructures of scalars and vectors, we can directly perform virtual state engineering, and this allows us to directly engineer the so-called laws of nature of the normal observable laboratory state and thus engineer and change physical reality itself. In the new approach, we can, observably, have 2 plus 2 not equal to 4, or 2 plus 2 equals 4 by the following means. In the first case, equation 36, we assume that the virtual substructures are patterned, and interact nonlinearly in such a way as to produce an extra observable. Thus we have a delta added to the normal observable scalar results of the interaction, as follows. Where subscript O means observable and V means virtual. Note that indicates a delta due to virtual substructure interactions yielding an extra observable delta. This extra delta may be either scalar or vector in nature, depending on the circumstances and the particular interactions. Note also that any vector or scalar must now be considered to have, contain, and consist of an infinite substructure. And note that, similar to the scalar case, from the new viewpoint the present theory assumes each scalar, point, of the vector to have a structure similar to that of equation, except that now the scalars are ordered, with a linearly decreasing internal stress density per unit scalar along the line of the vector. In the new approach, vector interaction, superposition, for example, can now violate present theory, if the two virtual substructures interact nonlinearly to produce a non-zero, observable delta. Observably, macroscopically, this delta, again, may be either scalar or vector. This approach now becomes consistent with quantum mechanics at the foundation level. Substructures, virtual levels, and hyperspaces. In the new approach, our definitions and assumptions immediately drive us to a picture of an infinite set of nested levels of substructures in the virtual state. That is, any one component, scalar or vector, in one level of virtual state has an infinite number of even finer virtual components, one level more subtle. And that is what particle physics and quantum mechanics already reveal about the structure of physical reality. So these definitions and assumptions now provide the basis for a new vector mathematics that is in accord with, and fitted to, modern physical observations. We have a picture such that any observable scalar or vector contains a virtual substructure, virtual level 1. Any scalar or vector in virtual level 1 also contains a finer virtual substructure, in virtual level 2. And so on ad infinitum. Each succeedingly finer level of virtual state can be modeled as a hyperdimension, higher spatial dimension, as I pointed out in Appendix 1 to my book, The Excalibur Briefing. Thus this approach immediately ties into hyperdimensional or hyperspatial theory, such as Elizabeth Rauscher's 8-dimensional theory and C. Muses's hypernumber theory. The new definitions and assumptions are far richer than what is allowed by tensors, though there are many similarities. Muses's work, however, essentially can encompass most of these definitions and concepts, except the distinct types of vectors are not so clearly delineated in his theory, at least to my comprehension of it. His theory does provide a nested, hyperdimensional structure of time, however, and thus allows scalar waves in the hyperspatial structure of time, in other words, observably scalar waves in the virtual state structure of spacetime, or pure Tesla waves, or simply time waves. These are the bare notes, from this approach, already new, proprietary, mechanisms and exact specifications to make scalar waves, in essentially whatever quantity and degree desired, appear to have been successfully accomplished by my close colleagues. The new approach is real and it leads to a new physics. And I believe that the very beginnings of the new physics are already working on the laboratory bench. Nikola Tesla discovered the most essential features of the new electromagnetics over 80 years ago and was simply suppressed for his efforts. Now, although it has been 80 years in the reborning, Tesla electromagnetics is once again loose in the Western world. This time, let us hope that it fares better at the hands of orthodox science and large financial control groups than it did for Nikola Tesla.